All right, how's it going, everybody? We are here on February 12th. It's Friday. We are going to talk about section 2.2 today. We're going to look at geometry of systems. This should be pretty brief, but we do want to introduce some important notation, and we do want to see some use of technology today and how we want to use technology to help us get a little bit more information. But we also want to see how the technology we've been using is actually slightly limited in that sense to get a little bit more motivation for the word directly above my head right here for the programming unit that will be starting next week here. So kind of our next things happening here is we're talking 2.2 today, geometry of systems. Again, it's just going to be like notation and a little bit of technology discussion. This will be pretty short. Next week, when we look at section 2.3, we're going to see special cases of systems. And what we mean by special cases of systems is we want to say, are there any systems that we can solve like without actually learning anything new? And so that's what we're going to cover in 2.3 is saying, just based on chapter one, what systems can we solve? And there's going to be a couple of them that we can. The general case of a system of differential equations, though, is still going to escape us, which is why we're going to then head off into chapter three to get a more general setup for solutions of linear systems, as we'll come to define them. And then after we do our 2.3, that's when we're going to get into 2.4. 2.4 and 1.4 are both the programming sections. So that's where after 2.3, the day after that will be sort of like section 1.4. The following week we'll do 2.4. We'll also look at a couple other special topics I'm going to throw in here for programming. So we'll spend about 3 or 4 videos doing some programming things in Python, starting with our second video next week. So geometry systems again today. Hope this would be a pretty short one right here. I also will say I have a leaky roof, and there is supposed to be a repairman coming sometime, as it always goes in like a 4-hour span. And as it often goes, it ends up being right at the time that you don't want it to be. So I'm hopeful that that will be after I am wrapping up this video, but there's a chance I might have to cut short here and kind of deal with that here, but hopefully not. So let's get into it. Basically, in the last section, we saw these phase plane diagrams, and what we want to look at today is how are those actually produced, and what different notations should we be using associated with our systems to be more reflective of the graphs that we're actually seeing out here. So, in general, a phase plane is a more special case of something in general that we call a vector field. And you have seen that when we go to graph these phase planes, and I guess I could just pop over right now. Actually, this one's different than the other one that I was looking at there. That's okay. Oh no, never mind. Excuse me. It is the same. Notice here that all of these are arrows right here, right? These are arrows that are indicating direction. These are really vectors that are in space. However, these vectors have lost some information along the way, and that's what I want to distinguish between right here. When we say that that a phase plane is a special case of a vector field, is a vector field, the difference between the two is that the length of each arrow or vector is proportional to the magnitude. However, because it gets really, really difficult to read the graphs when you have arrows that are like super long and arrows that are incredibly short, the very standard thing to do is to draw phase planes where all of the arrows are the exact same length, regardless of whether the magnitude of the vector is large or small. Right? So in a phase plane, all the arrows are the same length. This makes it more readable so that we don't have like massive or tiny vectors out there, but there's a loss of information. And basically, these statements right here motivate everything that we're going to talk about today. One, we want to be thinking about these systems of differential equations in a vector format, since that's how we're visualizing the solutions graphically. So we're going to convert into some vector notation. The other thing that we want to talk about today is we're losing information when all of our vector arrows are the exact same length all the time. And so we want to see where can we sort of recover that little bit of information. And the answer is going to be pretty mediocre in the phase plane plotter that we've been using from the bluffton.edu site. It does some good and some bad things for us. And that all that's going to do is provide us more motivation for in our programming section to do a slightly better job than the website is actually doing producing graphs, to be more interpretable on our end here. So last section, we looked at this rabbit and fox predator-prey model. And what we want to do in this case right here is we want to be rewriting this thing to really be in terms of of some vector type notation right here. So what we're going to do is we're going to rewrite this as the vector. And in this case, I'm going to use P for predator prey. We will use different letterings for this guy right here, but the important thing is I'm giving it the arrow hat right there to indicate that this is a vector. And the vector that we're considering right here is the vector r of t, f of t. And since this is r of t and f of t, you should notice that's actually what our hope is to be able to solve for in this differential equation right here. So this would represent our solution curves. Right. If we're thinking about r of t and f of t in that vector form right here, then we should notice that we should be able to write things like the derivative of that vector p with respect to time is the same thing as the derivative of r of t with respect to time and the derivative of f of t with respect to time, which we are writing here as exactly the equations that we can see. So there's nothing really different that we're doing right here, but we're introducing new notation that's going to help us think about how are we ever constructing these phase planes. And this is really important thing to do to sort of like make our work match our graphs rather than the other way around, because so many systems we're never actually going to be able to solve. We're only going to be able to analyze them graphically. And so it matters more that we build our notation to suit our most common analysis method, rather than saying, oh, a graph's just one thing. It's kind of our primary thing now. So we're going to build our notation to match it up, right? So here we're building a vector p of t for our solution curves. The derivative of p of t is the individual derivatives of the solution curves, which is exactly our differential equation right here. And so I've just got our two differential equation expressions sitting right there, right? What we want to do is we want to think of this right-hand side as a vector at the location rf, right? So what this means to me is I can rewrite this then, so maybe some different notation would be the vector field at the location rf, right? This is like writing something like f of x, except the input into the vector field is a vector, not an ordered pair. Slightly different, right? The vector rf, it's a location there. And this is going to be our 2r minus 1.2r rf, negative f plus 0.9 rf. And what this allows us to do, and by the way here, I'm just going to say so this is just to say, is my like little note on the side right here. I'm sort of picking an arbitrary variable right now, but I'm just telling you, I'm using v right now to just stand for like vector. But later we're going to want v to be velocity. Later we won't be talking about rabbits and foxes, and so f will become available for us, and we'll typically be doing this. And like I kind of verbalize it as like an f of x type of thing right here. So don't worry too much about what letter I'm choosing, but understand very importantly that the arrow notation is indicating that I am expressing a vector. Not a function, not a variable, but a vector with that arrow hat right there. That's kind of our important thing. So the thing that we can now do is we can now talk about what should the vector look like located at a certain location, right? So if we are at the location RF being 2, 1 in the vector plane, in the phase plane out there, then I should be able to write this as the vector 2, 1. RF is 2, 1. And I can go ahead and evaluate what we're going to get right here, right? This should be 2 times 2 minus 1.2 times 2 times 1. On the bottom, I'm going to get negative 1 minus 0.9 times 2 times 1. If I go ahead and evaluate this guy, it looks like I'm getting 4 minus 2.4. I'm getting negative 1 minus 1.8. And so it looks like I'm getting the vector 1.6, negative 2.8. So what that tells me is that, oh, wait a minute, did I? Oh, I see what I did. Here's my little tiny mistake right here. That should be a plus sign. It's a plus sign right there. That's a plus sign right there. I should be getting positive 0.8 right there. I was like, that's not what I remember. There we go. So what this says to me then is at the location 2.1, or sorry, not 2.1, 2 comma 1. If I go to 2, 1, that's R, that's F. This is the location that we just evaluated what vector we should be observing. That's the 2, 1 location. What vector should we be getting? We should be getting one that points 1.6 units to the right. Guess I can draw a couple more down here. And goes 0.8 units up. And so there is the vector that we have just computed right there, right? That is exactly that vector right there. This 2, 1 is exactly that location right there. And I'm going to blow up that vector a little bit right there just so we can see it. All right, I'll draw it the way I drew it right here. I'm going to get some dash lines going on. This is the location, 2, 1. This is 1.6 units to the right, point units up right there. Those were changes in the R value and the F value, right? Remember, our differential equation literally says, what is the change in R? What is the change in F? Well, if R and F are currently 2 and 1, then over the next 1 unit of time, we should expect R to change by 1.6. It does. We should expect F to change by 0.8. It does. And therefore, the vector that we should expect to see in our vector field should be this guy pointing at exactly this angle right here. Now, again, as I said above, our difference between our vector field and our phase plane is that in the phase plane, all we're going to end up actually maintaining is just the direction of the vector. If this were truly a vector field, we would exactly keep the appropriate length of it as well right there. But again, what ends up happening is that a lot of times you get some vectors that should be technically like as long as the whole screen, other ones that should be this short right there. It ends up making things either way too cluttered or like you can't even see the vector because they're so small. So a very common thing to do in phase planes is to make all of the vector lengths the exact same length so that you get all of your ideas of direction, but we've lost our ideas of magnitudes of these directions. How much change should we experience in 1 unit of time? You can't read that off of our graphs from our anymore. You know what to experience in the long run, but if I were to say to you, hey, about where do you think we'll end up in about 5 units of time? You have no idea how far along any of our solution curves we're really traveling just by looking at our phase plane graph, right? That's the loss of information. But again, it's a trade-off that people have just decided is in our benefit right there. And more easily visible graph about what the change is, not about how much the change is, right? So we're keeping direction, but we're losing magnitude when we transition from a vector field to a phase plane. So when we graph phase planes using technology, what they're doing is this. Step one, they're creating a mesh grid of points within the specified spans of x, y. And what I mean by that is we're just saying if we wanted to go like out to 4 and out to 3, then maybe what they're going to be doing right here, if that's like our region of interest, is it's just going to identify what should be like a grid of points. It's a mesh grid because it is a two-dimensional grid. It's x versus y. But we're going to identify like what are all the locations of interest where we would like to place a vector. Then it's going to evaluate what are the rates of change of X and Y at each of those locations in the entire grid. As I've drawn it right here, it looks like that's a 5 by 4 grid. There's 20 points. It's going to calculate what should be the value of dx dt and dy dt exactly like we just did right here. It's going to get that vector, and then it's going to plot the vector that we just drew sitting on each of those points right there. So this is just really a super repetitive process. It's come up with all of your locations that you want to graph a thing, graph a vector. Use your two differential equations in your system to determine how much up left and right, how much up and down we want to do for that vector, what's our direction that each vector is pointing in, and then go ahead and plot an arrow that's pointing in exactly the appropriate direction with the base of that vector arrow sitting exactly at the locations within the mesh grid right there. So it's actually kind of easy to produce this because it's like to do it once is easy. And if you're writing a computer program, it's also very easy to say, then repeat that process a billion times. That's effortless for me to write one extra line of code that says, okay, it'll end up being two different lines of code because it's one for each X value, one for each Y value, whatever. Really easy to make repetition happen when you're writing code. So as long as we can understand how do you do it once, it's going to be really easy for us to do it lots of times out there. That's kind of our point right here, all right? So let's do one of these. This is a thing we should never want to do by hand, but we can go ahead and draw a phase plane by hand that we saw associated with the mass on the spring in our last section here. So we won't, this is going to be pretty easy right here. We're going to get some nice, let me see, I think I'm going to want some more room right here. So let's go ahead and create by hand the phase plane that we saw last section associated with our mass on a spring, right? So we did our Hooke's law combined with Newton's second law. That gave us this second order differential equation. Remember that we then said things like, man, it would be really nice if we could relate acceleration to position. And we said, well, you know, there is actually a variable that does that for us. It's called velocity. So we converted this into a system by making a substitution. I said, well, I know that the derivative of position with respect to time is what we call velocity. And I know that the derivative of velocity with respect to time is exactly what we call position. And this should be exactly our, well, no, I am going to write it right there. Right, so this is going to just be our system, dx dt equals v. So notice that the derivative of velocity is acceleration. And if we solve our original system for acceleration, all I'm doing is subtracting x to the other side. So I get the negative x for my value right there. So this is really our system that is equivalent to our second order single differential equation right here, right? So this is our system of interest right here. It seems like we can now rewrite this guy in terms of our notation that we set up a second ago. As I said a minute ago up here, it's a little bit more typical for us to use like a capital F to denote the vector for our system right here. I just used V because we had foxes claimed. Down here we have velocity claimed, so I'm going to switch to using F right here, right? So we're going to get our F of xv is going to be our, it looks like it's just v negative x. Right? So this is our compact way of writing our system. And now what I would like to do is I would like to follow these three steps right here to try and plot the whole phase plane. I mean, and not the whole thing, like it's like how many arrows do we really want to draw by hand? But here's kind of what I'm thinking to myself. Just going to give myself a nice big, and I got to draw a big grid right here, even though we're not going to do too many, because I have to draw a whole bunch of arrows on it, not just points in space, right? So I got to be a little bit careful here. So what I'm going to do is I'm going to give myself a little bit of a mesh grid right here, right? And I'm kind of thinking to myself, you know, here's some points of interest to me right here that I might want to be plotting some things. So very technically, I'm not going to plot a full mesh grid in the sense that it's not going to be a rectangular shape. But I'm going to say for those, what do we got? You know, for 9 for 13 points right there. Let's see if we can come up with what the vector arrow is that looks like it should be sitting on each of those points right there. All right, and all we got to do to get all that information is just plug stuff into this guy that's right here. All right. So first point, easy point, 0, 0. When I plug in 0 for x and 0 for v, what do I get out? 0 and 0. So my first one's done. I've literally already done this point that's sitting right here. The arrow has a radius of 0, right? So I don't have anything to draw for that guy. So maybe let's do the ones that are in the box surrounding the origin next right here. So if I come here, my x value here is 0, my v value is 1. So if x is 0, if x is 0 and v is 1, then I should be getting out the vector. I'm just doing some substitution right here, right? That's just going to be negative 0, and v is going to be 1 right there, right? So I should be plotting the vector that's going 1 unit to the right and 0 units down. So there's the vector that's associated with that guy plotted at the point 0, 1. I'm going to do that for all these guys right here. Let's go ahead and do the axis ones first because those will be the easiest. Here I'm at the location 1, 0. When x is 1 and v is 0, I'm getting out the vector 0, negative 1. So I want to go 0 units left and right, and I want to go 1 unit down. Now let's do our next axis point right here. I am at the location 0, negative 1, 0, negative 1 should be giving me negative 1, 0. That says go to the left 1, don't go up or down at all. And now we're going to do the one on the other axis right here, and then we're going to quickly draw some other arrows so it doesn't look like I'm drawing bad shapes right here. We're at negative 1, 0. Negative 1, 0 should be giving me 0, positive 1. That says go up 1 right here. And you should notice that all of these vectors are exactly appropriate for the circle that we drew yesterday, right? We said that it was rotating in this direction. Well, you can just picture each of these vectors that are tangent to the circle right there. Those are the ones that we just drew right there, right? It totally matches. Our other ones right here, now if I'm at 1, 1, if x is 1 and v is 1, then I should be getting out 1, negative 1. That says go right 1 and down 1. I'm going to go right 1, and I'm going to go down 1, and that should be giving me a vector that's going in this direction here. If I am at 2, 0, 2, 0 will tell me 0, negative 2. Now notice the important thing here. 0, negative 2 really tells me that this vector should be 2 units long. And so maybe I'm going to say right here, apparently I'm drawing a vector field and not the phase plane because I am maintaining the length of my vectors rather than making them all the exact same length right there. Keep it on going here at the location 1, negative 1, 1, negative 1. I should be getting negative 1, negative 1. So we'll go down and to the left. Down here, we are at 0, negative 2. 0, negative 2 should give me negative 2, 0, which says go left 2. This guy right here is at negative 1, negative 1. Negative 1, negative 1 should be giving me negative 1, positive 1. So that says go left 1 and up 1. We're almost done. 3 to go. At negative 2, 0. Negative 2, 0 should be 0, positive 2. So it says don't go left or right, but do go up 2 units. Here we are at negative 1, positive 1. Negative 1, positive 1 is going to give me positive 1, positive 1. Go up and to the right. And our last one right here at 0, positive 2. 0, positive 2 is going to give me 2, 0. So that says go to the right 2 units. And I am hoping that you are in strong agreement that this is directly matching the circle shapes that we were arriving at yesterday. All of these vectors seem to exactly be points, like vectors of tangency in a sense, to any circle that might have that initial condition that's right there. And the other thing that I think is awesome about this, and I like that conversation is coming up right before we do our programming unit. What we've seen is that sometimes our graphs mislead us and that sometimes they do sort of the wrong thing right there. The reason that they're doing the wrong thing right there is because that h value is really, in a sense, a constant coefficient on the length of each one of these vectors. So all that's really happening when we're graphing our solution curves is they're computing that vector and they're saying, okay, for how long do you want to use this linear approximation as our motion right here? If h is very large, then we're actually going to do things like starting at this location right here of actually going just vertically by 2 units. But what we know is that this should be a continuously changing direction right here. That as soon as you've gone up even a billionth of a unit, that now there should be a little bit of angle provided to that. And we want to constantly adjust to get those circle shapes that we know that we should be getting from our parametric equations of sine and cosine that we arrived at in the last section. So when we have those larger h values, like the default of 0.1, it's doing large linear jumps, which brought us, if you remember, our phase plane last time was giving us those outward spiral shapes rather than those connecting shapes, because it was going too far before it recalculated what its next vector should be out there. That's the reason why we need to have those shorter h values, so that we're constantly recomputing what our new direction of motion should be. Like right here in this mesh grid, if we're just doing integers where we're not updating until we've got a whole integer amount, then we're going to get some pretty terrible approximations here, right? So we can see kind of how our error is introduced into our graphs by the length of these vectors right here. And again, you can kind of see this idea that since some of these arrows are twice as long as other arrows, I hope that you can kind of visualize the fact that it's very impractical for us to actually keep the appropriate lengths of all the vectors, which is why we don't draw vector fields and we draw phase planes, because as soon as you have vectors that are 5 units long, like everywhere, they're all laying over top of each other, and it gets really, really tough to read out there. So it's very rare that you actually see vector fields for differential equations. Slope fields are always more readable, but we're losing information about the magnitude. Again, notice here what's going on. I want to, again, before I move away, I want to compare this guy at 1, 0 and this guy at 2, 0. Remember that this is describing a mass on a spring, right? So what we're doing right here is we're saying, if I pull this guy to the right by 1 unit and release, what we should expect is small changes in position, small velocities. And that's what we're seeing with our small arrow, small arrow, small arrow, small arrow. However, if we pulled this mass on the spring 2 units to the right, you should absolutely expect to see, notice that this is basically a giant velocity vector because it's only vertical, right? Velocity is what's measured vertically. So this says at this location right here, we should expect to see, because we pulled it further on the spring, it's going to snap back harder and we're going to have faster velocities and we're going to go more extreme. We're going to go 2 units in each direction right there, right? So this totally agrees with our intuition about the mass in the spring, which is the further you stretch it in the x direction, the larger you should expect your velocity vectors to get. If you pull it really, really, really far, it's going to whip back off to the other direction and then keep on doing that very quickly, as opposed to pulling it a small amount right here, and then it's just going to sit there and slowly do a little back and forth. We've all played with a spring. We all have this intuition, right? So the length of those vectors do intuitively make sense to me for the physics system. It just gets unwieldy to draw vectors of their appropriate lengths in our phase planes because they end up either too big or too small a lot of the times, right? So back to a little bit of notation stuff here. The final thing that we're going to end up doing, and this is like kind of getting into the notation that we're going to use in chapter 3 right here, is just to take our very generic differential equation system expression right here and just to write this as just a dy equals f of y right here. And in fact, that's even a y vector right there, where the y vector is really x and a lowercase y right there. So that's a capital Y, right? I think for capital letters, is that an A or an O? I'm not sure. At least my handwriting's sloppy enough that you can't really tell right there. So this is our super compact notation right here to indicate an entire system of differential equations. We'll use this notation a lot more once we hit into chapter 3 a little bit right here, just because, as you can see, we're just got a lot more writing that's associated with these things. And so since mathematicians are the laziest people around, we're looking for the absolute least amount of writing that we can do to still convey the same concepts out there. So that's kind of the notation that we're going to use here. Let's go ahead and talk about this loss of information. The information that we're losing that we've been describing is that here this is a vector field and not a phase plane because I did maintain the lengths of my vectors, but that's not anything that we're ever going to see in our technology solutions out there. So what we're losing information as to what is the actual rate of change. Is the rate of change large at that instant of time, or is the rate of change tiny? I know what direction the rate of change is, but I've lost sense of the magnitude, right? Every vector carries 2 pieces of information, direction and magnitude. Scalars just hold magnitude, right? That's the difference between a vector and a scalar. So We can't tell how quickly our solutions are progressing through those curves. We know what the curve looks like, and I know that if I just let time go, it's going to traverse those circles with that egg shape from the rabbit and fox populations. But it's not clear to me, is it moving like maybe like really fast around the right hand side and then like really slow on the left and then really fast? Is it like doing like a little whip around here? Other things that I know is that that's exactly what happens with planetary motion. We don't travel in a circle around the sun. We actually travel in like an ellipse shape where the sun is at one of the foci of our ellipse right here. That was almost a really good ellipse. And what I know is we actually travel much faster when we're closer to the sun, and we travel much slower when we're further away from the sun. In fact, I think this is one of Kepler's laws that says that the area swept out in an ellipse will always be equal over any given amount of time. So that means to me that like this little like sector right there, if this is equal area to this guy right here, then this will be swept out in equal time as this much shorter one will be swept out right there. So when we are nearer to the sun, we are actually revolving around it much quicker and we're moving much slower over here. That's the type of information that we cannot see when we just look at a static curve in the phase plane. And so we want to ask ourselves, is there some way that we can kind of like recover that information a little bit right here, right? So let me kind of say this in a few more ways. We'll look at two visualizations of this. So while we know the X and Y locations, it's less clear the amount of time it takes us to get to those locations from any other place. Especially considering we're modeling things like mass on a spring, we want to know things like when is the mass moving quickly and when is it moving slowly. What I kind of know, again, intuitively from this, is that when we are at the most extreme parts right here, that's when it's turning around, right? So that's when my like velocity is almost zero right here, but my position is large. When we are passing back through our point of rest, that's when my velocity is going to reach a maximum, because as soon as it goes past it, it's now being resisted by the compression of the spring, but my position is at a minimum, right? So our speed of that mass is not exactly equal. It's not going exactly back and forth at the same speed, constant speed all the time. It's speeding up, it's slowing down. It's slow at the edges, it's fast in the middle. Slowing down at the edges, fast in the middle. So given some small change in time, delta t, and an initial location x, is the value of delta x large or is it small? Are we getting a large change or a small change over a chunk of time? So I want to show you a graph that technically is some differential equation stuff right here. It's not directly related to the problems that we've seen so far, but it's going to give you the visual that I'm just sitting here doing a bunch of hand stuff right here. Let's look at a Desmos graph that's actually going to be nice for us right here. So let's pop over to Desmos here and see this guy. So here is a parametric curve, and you can see that our solutions that are coming in from like, oh man, this thing, oh, I didn't think it actually graphed out that far. So what we can see is that this guy right here is traveling very slow when it's near the origin. It's traveling super quickly when it's far away from the origin, right? The point is that every time that we plot something using technology, all you are seeing is the solution curve. The information that we've lost is, are particles that are traveling along the curve, are the rabbit and fox populations, is the mass and velocity of the spring changing rapidly, as we're watching happen on the edge of this spiral, or is it changing very slowly over time? Here, the change in time in this graph is a linear change. Time is moving at a constant rate all of this time right here, but very importantly, we're seeing it move very slow at the origin, very fast on the outside, and I'm going to say it for like the billionth time now, we can't see that distinction when we just look at the red curve. The red curve just looks like where it's going to eventually go. So you could say things to me like, oh, I know that the limit as time goes to infinity will tend towards any initial condition resulting being at the origin. I know what the long-term behavior of any initial condition would be associated with this system of differential equations, but it's not as obvious to me that it is rapid motion far from the origin, slow motion near the origin, and it's very possible that's a very relevant feature for us to consider. So this is our kind of visual so that I'm positive now that you all understand what I mean by fast and slow speed of solutions right here. Is our delta x and delta y large or small given some location in space? We can see fast delta x, delta y, small delta x, delta y over the same delta t intervals. Over the same interval of time, we're getting lots of change, or sorry, lots of change on the outside, minimal change near the inside right here. So let's go ahead and see this in our other plotter over here, right? So let's go ahead. There's an example here that the book proposes, but they don't do a great job of telling us where we should look. I screwed around with these initial conditions last night quite a bit to find some ideal ones right here for us to be examining right here. Um, and so let's look at the phase plane of the following system and see some nice things and some not so nice things about the phase plane plotter. I have a major beef with one of the graphs that it's going to make for us right here that I don't like, and we will do a better job of that when we go to do it in 2 weeks here. So before we do that, I just want to ask real quickly, where are the equilibria for this system here? Um, and I think I can do that pretty quickly right here. I think I can set dx dt equal to 0 and dy dt equal to 0 to get this simple system of equations right here. I can solve this pretty easily. So it looks like xy equals 0, 0 is our only equilibrium location right there. So I think the origin is the only, and man, you can see that super easy. Make x and y 0 and 0. Obviously, dx dt, dy dt are both 0. So that's going to be our one equilibrium location. The question is, to me, near the equilibrium, are solutions moving fast or slow? And here's something I can see right away. Notice that if we check out the points like 5, 5, far from the origin, when I look at 5, 5, I'm going to be getting dx dt is going to be 20 right here, right? 15 plus 5 is going to be 20. Dy dt will be 0, but this suggests to me there should be a massive vector pointing directly to the right, a 20, 0 vector right there. And it should be 20 units long, which it won't be. It's just going to look like an arrow the same unit as everything else. On the other hand, if we look very near to the origin at like 0.1, 0.1, then you should recognize that we're seeing vectors that are of length like 0.4 in the x direction and again 0 right there. So near the origin, that vector right there would be like less than 1/40th as long as the one that would be at 5, 5, the one that's at 0.1, 0.1. We can't see that right there. So I think that our solutions are moving very slow near the equilibrium right here just by comparing 2 points. Let me just say here, um, so let's go look at a trajectory that will pass near the origin and see how we can see what's going on in our technology stuff that's over there. So I'm going to pop on over to Bluffton. I'm going to throw in this differential equation and I'm going to ask it to plot the one solution associated with this differential or with this initial condition. And obviously this is a kind of ridiculous x value that's right there. This was just me like playing with numbers a bunch of times until I got one that got as close to the origin as I could possibly get it to go. So let's come over here and do that here. So 3x plus y and x minus y are the two of interest. So, oh, right there. 3x plus y and x minus y. So there is our slope field for this guy. I don't want to go too quickly into just what I said, right? That's very narrow. Let's click a bunch of times and see what happens. Oh, by the way, I know that I never really want that to actually be that guy right there. Let's at least do this guy right here. Um, and so what do I see right here? What is happening near the origin, by the way? It looks like things are sort of... This is kind of weird, actually. So check out this behavior near the origin as I do this. It looks like there's some like line that's right here on which the solutions seem to be moving like towards the origin. But it seems like as they get close, they're like splitting and like running away from the origin. So this is weird because it's like, I mean, you can see right here, things are starting off moving towards the origin, but then getting pushed away. Again, I am really not sure how I'd classify this yet. We're going to classify this guy in chapter 3, looking a little bit more closely at it. But this is weird because it seems like things move towards the origin if they're kind of along on this, whatever this one path is right here on this line. But then it seems like they get pushed away, and it seems like they then fall onto some other line out here that they're getting really close to. So again, I'm kind of struggling to classify that equilibria right there. But that's what chapter 3 is going to be all about. So now that I've kind of just like And whatever. I do appreciate the fact that it's like every time you graph something, it's just like, okay, go ahead and click 1,000 times over here to get a general idea of the flow of these things over here. But again, the thing that we've learned is that these guys near the origin should be much, much slower in their change than these things that are far from the origin. I know that from just very easily just plugging in some points into this and seeing big numbers, big vectors, and seeing small numbers give small numbers, small vectors right there. So I'm losing that information, right? So let's go ahead and plug in that kind of ridiculous initial condition that I gave right here. The initial condition that I gave was negative 0.7082 and a y value of 3. And the thing that this one's going to do nicely for us is it's going to, oh, and by the way, I'm going to update this to RK4 as well, Runga cut a 4 right there. And I think I'm going to make this even a little bit smaller right there. I don't think switching will do anything for us right here because we're not going to see closed orbit solutions ever. But I'm going to click it anyway because I know that clicking it won't ruin anything if I do. Switching is helpful if you ever expect to see solutions that are forming like a closed loop, like some of the ones that we've previously seen do. Um, we've seen those ones that get that weird like jagged back and forth. That's fixed by the switching checkbox getting clicked right there. So let's go ahead and see what happens here. All right. So what we're seeing is that this solution here is starting at this kind of weird negative zero point 0.7 whatever 3. So there's our initial condition that we plugged in up there. And this curve is taking like a straight line path. Man, that should be weird to you. It seems like our solution curve is like a straight line, and then it gets really close to the origin here, and then it shoots away along another seemingly straight line. Those straight line things are going to be of heavy interest to us in section 3.1 and 3.2. Heavy interest to us right here. But what we can see is that the reason I'm picking this initial condition in particular is because it's one that brings us super duper close to the origin right here. So what I want to ask myself is, if I didn't see this differential equation, I want to still say like, I don't know, or if I didn't understand like plugging in points, I want to say, can I kind of like visually see if we're moving fast or slow near the origin? So let's go down to our secondary graphs down below here, and let's see the good and the bad news. So I'm going to bust this thing open right here. So here's what I can see. These are my graphs of the individual solutions x and y. I don't know what the equations are for x and y, but numerically we can estimate that whatever the equation is, the curve should look about like this. Here is the good news, and here is the bad news. Look at the red curve. I see a really, really flat curve right here, and when is this curve flat and not changing much? Right when I look over here and see the value of 0 for the red curve. It looks like as our x values get close to being 0, they are not changing much. Very, very slow change. Low slopes over here near 0. Once we get far away from 0, we have steep curves. X is changing a lot when x is far from 0. X is changing a little when x is near 0. Here is the worst thing that's happening on this page. What's so hard about making one common y-axis? My goodness. I can't believe how nice this overall website is, and then it's doing this to me. It looks like these two graphs are like separated from each other right here, but they're not. The blue graph's y-axis is measured differently than the red graph's y-axis, making them not directly comparable. What I can see if I go back up right here is our y values are never negative. Our y values are always positive. And if you come down here, recognize that the blue curve is the y curve. It does dip below the red curve, but notice on the blue axis down here, it really looks like the bottom of the graph is 0, and this never dips below the bottom of the graph. So again, what I'm seeing here is it also seems like our y values change a lot. They have a steep slope when they're far from 0 on the blue curve, but as the y values get closer and closer to 0, they just don't change much. Look at this. Over all this time right here, the y value essentially didn't change at all. There's this much change in y for this much change in t, right? It's very slow changes. On the other hand, over here, just small changes in t produce very large changes in y. So we have fast solutions here for y, fast change in y, but we're noticing it's actually kind of small changes in x at that location. Near zero for both. Now, the very unfortunate thing is that these two guys right here are almost at 0, 0 where I have my mouse. It looks like X is almost zero and Y is almost zero, but that's really hard to read because for some reason the Y axis isn't the same. So when we go to write our own code for this, absolutely we will have one Y axis measurement so that we can directly compare these two graphs. I don't know why they have to be off by like a shift, and they're not even like off by a shift. Like the scaling is also different out there. And this is like so close to being exactly what I want. Check out this other nice thing over here, though. Last kind of thing I want to show you is in this table over here, it shows us at what X and Y locations we're at, how much, what is the delta X and what is the delta Y for that given T. We can see that our changes in T for every row of this, delta T is apparently 0.005. Oh my gosh, how did I know that delta T was 0.005? It's sitting right there. Right? It looks like what our H is actually measuring is how long, literally for how much time, should I just go in that one direction that the vector says before re-estimating a new direction that I want to travel from my next vector, right? So this is, every curve that we see out here is really just a bunch of straight lines being glued together out there. You should be thinking about things like from Calc 2 when we did our arc length. Arc length, the integral formula for arc length is just the sum of a bunch of straight line lengths where each straight line is infinitely short. What we kind of want here is h to be infinitely small. Then we do get a true perfect solution right there. Just that we can't do the computation that's associated with it. But check this out. What we can see here is how much x change and how much y change do we have at a given x and y location. So here I'm seeing things like at our initial condition, X is changing by a pretty small amount right here, but our Y is changing by a bit more moderately large of an amount. And recognize that this is a very small time interval, so I am expecting to see also pretty small X and Y values right here. But watch as our X and Y values get closer and closer to zero. I'm going to scroll down now. So I'm watching my Y values here. They're at like 2s, 1s. Notice here we're at like 1/3 for X. We're at like 1.5 for Y. I'm going to keep going. I'm going to keep going. And it looks like now I'm seeing these values for the X and Y column are getting smaller and smaller and smaller. Keep scrolling, keep scrolling. I want to see where they get down to actually being like, where's Y's minimum? Like maybe that's a point of it. Okay. I'm seeing that X actually kind of just reached a minimum right here, by the way. Where's X's minimum? Wait a minute. Did I? Oh, that's right. The X is always increasing the whole time. Um, but it should have started out negative, right? Oh, okay, okay. So here is X very, 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 this is my closest X to being zero right there. And notice that when we're near zero, my delta X is also essentially at almost a minimum right there, right? We're getting these really, really, really tiny changes in X when X is really tiny. Now, change in X is also dependent on Y, which is why this is not truly the actual minimum change in X right here. But we're also noticing that as our Y values get down to being a minimum right here, it looks like our Y value reaches a min. See, the smallest Y value I can see is like these guys, right? Like a 0.86. Is that true? No, 0.85, 0.84. Here we are. I think that the smallest Y value I can find in this whole thing is about a 0.084. And we're noticing, oh man, like look at how small that change in Y is right there, right? So we are seeing from a table perspective here, this idea that small x's and small y's are giving small change in X and small change in Y. So even just in producing this table, oh yeah, ignore all the K's for now. All of these K's are coefficients that we are going to be computing ourselves in association specifically with the Runge-Kutta-4 method. If we switch back over to Euler's method, none of those are relevant there. So these are coefficients that are associated with this particular technique that's right there, which is why I don't want to look at those yet, since those don't mean anything to us yet, but they will in a few weeks here. Kind of. We're not going to like study each of those individually or anything like that. But again, what we want to see here is that we can see the flatness of our individual solutions, suggesting slow change over a period of time versus steep parts of our individual solution curves, which indicate a fast change in our solution over time out here. So that's just kind of the stuff that I wanted to look at here today for these guys. Nothing too crazy, but I do want to express to you, one, you should be expecting that we're going to be using a bunch more vector notation coming up here in the following months, honestly, because everything associated with systems, we should be thinking of our graphs as being like a vector field. for our phase plane, and therefore we should be using vector notation to represent our systems. The other thing we should be seeing here is we gotta know in what ways we shouldn't trust our technology. The two ways I know that I shouldn't trust my technology is that sometimes we should see things that are like closed orbits, like we saw last section, that sometimes if our H value is too big, actually ended up looking like spirals. And that wasn't right because our approximation had a lot of error in it. That's one thing we're going to learn to not trust. The other thing that I'm learning to not trust is that since I'm never going to see the actual lengths of my arrows in my slope field, it's always our job to work to understand, are the solutions changing quickly or are the solutions changing slowly at any given location on that solution curve? And again, I would suggest that you should just like kind of keep this graph in mind right here, where there's the fast moving parts and the slow moving parts. And you know that that's a thing that can absolutely happen with our parametric equations. A constant change in time is not a constant change in length around the parametric curve right there. And so just kind of recognize like, what is technology doing for us, but what isn't technology doing for us? We have to know where our brain has to fill in the gaps that technology is not filling in for us when we view things like our slope fields that are up here. We have very slow motion here. We have fast motion on the edges. And all I want is just to be able to click play on this dot right here and watch it go fast, slower, 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 take like forever to get through here. But once it gets through here, it's going to get shot out to the right? There's more information in this picture that we don't get to see, and it's up to you to be able to deduce that information based on plugging in some values into your differential equation, looking at your individual slope graphs, or potentially even consulting a table of delta x and delta y values. And again, we're going to produce all of this. This picture we're going to make, okay, there's not going to be the arrows on it, but these curves we're going to make, these curves we're going to make, these tables we're going to make. It's all coming up in 2 weeks right here. And so we'll be able to kind of pick apart this stuff a little bit more right there. So again, today's lesson is really just new notation and know what your job still is associated with technology for gleaning a little bit more information out of these graphs that's not directly visible in them. That's all I've got for you here for 2.2. Remember that where we're going with this stuff is that next week we're going to be looking 2.3. We're going to solve all the systems that we can solve only using chapter 1 knowledge, just to get those out of the way. Chapter 3 will get all the rest of our linear systems. After we're done covering 2.3 next week, our first video next week will be our first Python programming video where we're going to start building some of our approximation solutions. So that's actually going to be section 1.4. 1.4 is going to be our second video for next week. 2.4 will be the video after that. Then we'll also look at a little bit of stuff in chapter 7, which is the Runge-Kutta-4 method that we've been using at Bluffton, as well as just another thing that's not in our textbook that I think is at least worth looking at to kind of tie some stuff together out there. That'll be really cool. So programming starts with our second video next week. 2.3 is just us applying chapter 1 knowledge to systems of differential equations. It's not any new techniques. It's using old techniques in new situations. I will see you guys for 2.3 and the start of programming next week. Have a good one.